Okay, so last lecture of the day is by Inhyeok Choi, and it's his third lecture. Right?
Okay, so thanks for sticking to the last lecture. But before the lecture, two announcements. Actually, one announcement, one news. First announcement is still India has put so many efforts, like really tidying up the class. So please come, either play or enjoy the play. Okay, so it's happening this evening. Yeah, supposedly this is here. Second thing is, among the audience, I think Shake-It is her birthday, so I'm supposed to celebrate. Yeah. I mean, this is more important than math, so yeah. Whoever whose birthday is nearby, just let me know so that I can, yeah. Just text me, okay? Yeah. Okay, now boring things. So yeah, I kind of promised to you that we're gonna show some results about closed curves or closed geodesics on surface, and actually we'll prove this result in quite a best generality. So it'll be in the end, you might well forget about anything about manifolds, but it's just about group actions on some metric space that has some hyperbolicity. So how you can interpret this in a multiple ways. But just for picture, this is our object. So we want to describe how many curves we can draw on the surface if you're given a threshold. So just to remind you the notation, this is too lengthy, so I just abbreviate it as PR. And so there's a remark that we divided the task into three steps, but the first two steps were really not regarding the contrasted class or the closed geodesics that I promised, but this is really regarding group elements whose orbit points are within the designated threshold. So the first two steps are really regarding orbit counting, but the third step is really regarding how to relate the orbit counting and closed geodesic counting. Hence two sets. So let's recap. So last time we wanted to see these kind of things. First, we wanted to see that, so the setting, G is acting on X. This is, right now, in general, it's geometric metric space, but this is, for now, delta hyperbolic space. And the action is proper and co-compact action. And the first step was to show that this quantity exists and is positive. And the second step was, so this is basically, so to rephrase it, so this is we want to estimate this number. This is bounded by two functions, where this is exact exponential function, but this is bounded by two functions, but okay, I will write like this because for some sub-exponential f. So if you take the log and divide by r, then you will see this. But the second step was improving this estimate. So we wanted to actually show that there are two constants. Actually, the discrepancy from the desired ideal function is just the bounded constant. So we wanted this kind of estimate. And final step was to prove that This is also in a similar sandwiching situation, but now the function is divided by r. Okay. So last time we checked this and this lower bound, but before proceeding, this is such a mistake that hyperbolic surfaces are great. And I mean, this is the simplest example that I can bring, but there's even more like simpler example that I missed. So I brought one. So what is this? Yeah, this is what I don't usually write, but this is something related to the free group generated by two elements, A and B. So what is this diagram? This is the diagram that Piotr taught us. What is this? So in so what is F2? F2 is really a collection of a bunch of words. But these words should satisfy some rules. So, I mean, you can take arbitrary like words made by A, B, and A inverse and B inverse, and you can take the equivalence class. That's fine. But if you want one representative for each element, then you want to generate words like without cancellation, like without further cancellation possible, right? So how should you generate a word? This is the rule. So you first go to either A inverse, or B inverse, like whatever. But then if you had, oh, sorry, is this, no. This is terrible, sorry. Yeah, this should be like this, sorry. So what's the rule? So suppose that you have walked to A, and then like this is the first word that you have obtained, like at step 1, you generated A. And then what's the second step? You can generate either AA or AB or AB inverse. They are totally legit, but AA inverse is prohibited. So next time, if you want to go to distance 2 from distance 1, then you shouldn't add A inverse. So A inverse is not the next letter. Only the 3 other letters are valid. And the same goes to other letters that you have chosen as step 1. And that repeats forever and forever. So if you have walked to like AB, then the next letter shouldn't be B inverse, but all the other things are valid. So basically, if you follow the arrows like for finite times, then you will get some words, and this is the this is how you generate all the valid words for F2. So why did I brought up this? Let's consider the first task and the second task. So I will remind you. So for the first one, I used the Bechet's lemma, which is regarding subadditive sequence. But if you're really dealing with F2, then probably you don't have to bother with that. Why? Because it's not only subadditive, but it's really additive in some sense. How can I say like this? So for the first step, the ingredient for the first step was like so. So if you want to generate a group element at distance, let's say in Bn plus m without any error this time, then you just draw the geodesy and you just pick the one at distance n from identity. Then there is a group element. Why is this so? This is because for F2, we're dealing with Kelly graph, the graph with like edge length O1. So if you draw a geodesy, the vertices are already there. The orbit points are already there. So there's no error whatsoever. So this case, it's really like this quantity is, I'm cheating a bit, but this is not really a cheating. You can really say like so. So what is the cheating? There are 4 generators for F2, right? But each step, you can only add 3 valid letters afterwards, right? So you should really forget the number 4, but 3 is the really valid like constant that matters. So the growth rate is really 3, not 4. Hence, up to the discrepancy that happens in the beginning, in the first step, like it almost adds up. Like it's almost multiplied, and if you take the log, then it's even not. So what I'm meaning is, this basically means, so from this, you'll be able to deduce that this is constant if this happened. Okay, for now, yeah, there's a matter about like the first step, but if you build for the case that this happens, for example, if you're dealing with like free semi-group instead of free group, then this is really as is. And for free groups, okay, you should modify a bit, but that's not a big deal. But if you're dealing with general like group actions on metric space, it's not guaranteed that the geodesic connecting orbit points are seen by the orbit points in between, but they're only within bounded distance. Why is this so? Because we're acting on a co-compact. The action is co-compact. So what I'm telling is, if you're too bothered to consider just like manifolds or like delta hyperbolic space, then you can just stick to F2. And then what we're doing is just doing the simple combinatorics in a more complicated way. But the philosophy just persists. Okay. So this is this generally holds for co-compact group action on a metric space. So there's no hyperbolicity whatsoever. For the item 2, so lower bound was already achieved because of the Fekete lemma. Now we're trying to establish upper bound. How do we do? Again, the lower bound came like immediately because it was an inequality, but there was no reverse inequality guaranteed for general metric space, general like group action. Hence, we had to like argue further. But just imagine, if this is really equality, you don't have to even care about upper bound, because like this is really not important. This will be just constant times exponential function. So this is the ideal situation, and step 1 and 2 is just immediate. But in general, it's not the case. So what's required? Let's see. So to establish upper bound, we need some kind of arguments like this. Let's say, so the plan is, or the hope is, towards the contradiction, if we had something like this, then this, we hope that this implies the cardinality of the k times r radius ball is exceeding what it should be. If I can deduce this implication, then this leads to the contradiction, because this is exceeding e to the hr that it should have at step k, right? So what I mean is, if it's like so, then this will be 1 plus like this, and this is, you can also say this like e to the h times 1 plus epsilon prime times r. So at the end, you should get the limit h, but you will actually get h plus something, which is the contradiction. So this is the plan of the proof. So in order to achieve this, what we need is that receives the input, the finite sequence GK, where G1, GK are from B to the R. And then it sends this input to some element in BKR. So the domain of the cardinality of the domain is ER to the K. And if this map is injective, then we get the desired inequality that leads to the contradiction. So we need an injective map, but this is too good to be true. It's usually not injective, but it's only finite to one map. So we need an almost injective map from this domain into BK to B sub KR. This is not hard to achieve for F2. So I will first explain why is it. This is distance R, distance 2R, distance 3R. Let's say we want to, let's try to construct the ternary map. So I first get the input G1. Let's say G1 is AA. And then I want to generate, and I also receive input G2, whose length is, let's say, R, like AB or BA or like B inverse A, whatever that is. And also G3. And then I want to generate an element in the radius KR. So what is the most straightforward way to do that? It's probably the concatenation, right? Because if you concatenate like K progresses of displacement R, then the displacement is at most KR, so it's residing in the bowl. However, if you bring G2 something like A inverse B, then okay, this is erasing partially the information given by G1. So this is probably harming the injectivity, okay? So the point is, given G1, you force that G2 should begin from A or to begin with B, but not to begin with A inverse. Hence, if you had made progress, then the next element, for the next element, G2, you discard all the elements that's beginning from A inverse, but that begins with something else, some other letters. Then the concatenation will be like geodesy, right? There's no cancellation happening. And if that's promised, then you will also have the final letter for G2. And then for G3, you again require that G3 does not begin with the letter that cancels out the last letter of G2. Hence, you pick G1 from, let's say, BR, the entire BR. But G2 is not from BR, but a subset of BR. That does not cancel out the progress made by G1, which means the beginning letter of G2 is not like the inverse of the last letter. So this really depends on the choice of G1. So for example, if G1 was AA, then G2 S G1 should be those letters, those words not beginning with A inverse. If G1 was A inverse, then this subset S changes. But what's important is the cardinality is at least 1/4 of PR. Actually, you can make like 3/4, but it's not important. Important thing is this is uniform, regardless of R. And you can also require G3 to be chosen from yet another subset of BR, because cardinality is, again, greater than. So if you do this kind of construction for not all the sequences in BR, but some part of, like, some portion of, like, the sequences from BR, then the map is injective. What is the case? If you have two progress, and if they end up at the same point, then there's only one geodesic, basically, right? So if you chop them up into smaller progresses, they should all match. Hence the injectivity. So in this case, F is injective on BR. You should, like, this is really not a valid notation because SG1 is not a uniform set, but the nature of SG1 really depends on the choice you chose from here, and SG2 really belongs to here. But I will just say that it's a subset of BR to the K such that its cardinality is at least so this map is really this just purely sends this to the concatenation. So usually this is not injective map. For example, if G2 cancels out the entire G1, then it erases all the information. But if you restrict it to not so small subset, you can retain its injectivity, which is sufficient for our purpose. Because, yeah, please. Mm-hmm. Mm-hmm. So, oh, I see. Yeah. This is just a toy example. Yeah, for hyperbolicity, yeah. Now I'll go into that point. Yeah, thanks. But for free group, like, this is quite straightforward. Yeah, and this is partially why I brought up this, like, digress, because actually this construction precisely follows the machinery given here. So if you have walked through starting point through geodesy, can you elongate that into another geodesy without any cancellation? Can you do that? In general, like, groups like acting on hyperbolic space or even on their Kelly graph, you shouldn't expect this, even for hyperbolic groups. But for free groups and for hyperbolic groups, if you require that they follow only designated geodesics, not arbitrary geodesics, like, in a more fancy way, the geodesics given by the language from the automaton, then you can do this kind of job. So basically, if your group is given a finite state automaton that spells out geodesics in a one-to-one way to the group elements, then basically you can just execute this kind of strategy. So there is a theory for hyperbolic groups for that strategy, and there's an excellent reference which is written by Danny Caligari that I included in the abstract. So if you're interested in that approach, that's yet another approach to this problem. The first one was using classical dynamics, like in the sense of marvelous. But there's yet another, like, strategy, at least for hyperbolic groups, which uses the finite state automaton that's summarized in Danny Caligari's exposition. We're doing something else. Yeah. Now before proceeding, is there any other question? Now, as Zach pointed out, this is quite not the case for general action and metric spaces. So what are we going to do for actions on hyperbolic space? Recall that we can do this kind of job. We first fix two independent loxodromics. Last time the notation was unfortunate, so this time I'll be smart. It's phi and psi. Okay, now better. Then up to powering them up, we have the following property. First, picture comes. C is sending the base point in X to some direction, and psi is sending it to some other part. And if you draw a geodesic from x0 to any direction, that direction cannot fellow travel both progresses. That's pretty much the almost the definition of this independence of the directions in that type of space. So what do I have for any y in X? Either y x0 and phi x0 is, I'll be vague for this terminology, but you can plug in whatever like requirement you think. Y x0 is a line. So basically, if you have chosen y around here, then y x0 phi x0, oh, this does not seem to align. Like the angle is too acute, and it seems like the progress made by phi is canceling out the progress from y to x0. Yeah, that's true. But whenever, like, as soon as that happens, you have another choice to opt out. Okay. In that, for those y, psi will do its job. Psi will make this alignment. So this is one property. And second is the assumption is same. What's different? I just require it to be regarding the inverses. And why am I being vague here? Because, for that type of space, what do I mean by alignment? It means the ground product made by those like triples is bounded by a constant. So the exact statement is there exists a constant such that does not depend on the choice of y, such that the ground product is bounded, or this ground product is bounded by the constant. Okay, but I'm intentionally being vague because you can observe this kind of dichotomy in various other metric spaces as well. For example, on K0 spaces. So on K0 spaces, if you have two independent rank 1 directions, then you can always secure this kind of jobs. And we'll soon see, like, there are other metric spaces that you can also do this kind of dichotomy. So, yeah. But why does it help for the upper bound? So one lemma or one phenomenon in delta hyperbolic space that we saw last time is the following: the local to global property. If you have geodesics, gamma 1, gamma 2, gamma n, such that they are pairwise, not canceling out each other, then the entire progress is non-trivial. And what's more, if you take any middle point, like any intermediate point, then the ground product of the two endpoints of the sequence with respect to that intermediate point is still bounded. It's not, you will not see any like absurdly like huge cancellation. This was a property that you can secure on the type space. Yeah, there were some conditions like the ground product should be much smaller than the length of gamma i's, but let's just keep it aside. I'll just deliver the philosophy. Okay. And the consequence is these points are all within bounded distance from the geodesic that I drew here. In other way, if if the Gromov products are uniformly bounded, and if the lengths are sufficiently long, then this concatenation is a uniform quasi-geodesic on the metric space. Okay, why does this help? Now, we'll construct a map. Defining F. So given, let's say G1, G2, G3 in BR, we declare another group element as follows. So here is G1 X0. Either, okay, one of the four elements among Fi is from phi square, or phi psi, or psi phi, or psi square. Among these four elements, you can pick one Fi such that it's not canceling out the previous progress made by G1, nor it will not be the reverse direction of the G2 direction that it will make in the future. Why is this the case? If, let's say you chose V2, but you were unfortunate. Let's say V2 were like this, in this direction. Then you should have chosen the words beginning from psi, because psi will definitely head into some other direction and will not cancel out G1. So you're still safe. Likewise, if you have chosen like V2 and then like it was unfortunate, like it's canceling out G2, then it shouldn't, like your choice shouldn't have ended with V2, phi, right? Like you could have chosen some other words ending with psi. Then the angle will be obtuse. So among these four choices, you can always secure this kind of alignment. You can do the same game at F2, like after the progress by G2, and choose F2. That is not canceling out the progress made by G2, and also G3. Now this is the picture that you want. And this element, the G1, F1, G2, F2, G3, this is your F. Okay, so what's good about this? Now, if F, G1, G2, G3 were equal to F, G1 prime, G2 prime, G3 prime, what will happen? Let's say this word is W. By this property, G1 X0 will be somewhere around here. What I mean is, it shouldn't be around here. It should be, the orbit point should be close to the eventual geodesic. That is what we secure by guaranteeing this alignment. And also G1 prime X0 should be around here. Actually, the progress made by F1, this is fellow traveling some subsegment of the eventual geodesy, and also here. And you also have the same picture for G2 X0. And G2 prime X0. But you cannot like eliminate this finite amount of error. This is what you should really live with when you're working in the type space. If you're not in free group, if you're not in a tree, then this always happens. But that's not the problem. Why? This configuration guarantees that these are close enough. These are close enough to the same geodesic, so these are close enough. And within a bounded distance, how many orbits did we have? There could be several many, but there's a uniform bound of the number of orbit points you can have in a closed ball. That's the properness assumption, right? So G1 is almost similar to G1 prime. Okay, I should say like this. G1 inverse G1 prime is belonging to some bounded ball. And also you can inductively guarantee this kind of thing. So basically, this time you pick G1, G2 honestly from the entire BR. You're not shrinking these into a subset. But now, then you will lose the injectivity. But how severely you lose the injectivity? That loss is bounded. So this is how you guarantee the required estimate for the upper bound. I have treated one at one point, but before confessing, is there any question? Exactly. Yeah. Yeah. That was the point. Yeah. So I treated at a single point. That is exactly the case. So what if G1 was like here and G1 prime is like here? Then you cannot guarantee that they are within bounded distance, because if R is very large, then this could be as large as R, right? R plus some bounded amount. How can you prevent that? Now, to prevent that cheating, I should replace this with SM. What is SM? SM is, oh, sorry, this is PM. This remains true. But I should replace this with, okay, A. I will write like this. A R minus M R. What does this mean? This means the element whose displacement lies in R minus M to R. So pictorially, this is ball radius R, but you just make a thin shell of thickness M, and you just collect all the orbit points residing in the shell. This might sound a horrible idea because, you're losing all this inner ball, and you're just requiring G1, G2 to be chosen from here, then you're losing too much. No, it is not the case. Why? Because it's exponential growth. Okay? So if you take M large but bounded constant, then you can guarantee that the population of A to the A sub R minus M to R is at least half of the population of BR. So you're just losing bounded multiplicative vector, which is still fine for the estimate. If you require that, then the norm of the displacement of G1 and G2 cannot differ significantly. Then you can now argue like this. Okay, now no cheating. Is there any other question? Now we have upper bound. It's time to go to the conjugacy class. By the way, so there was this construction of map F, large F, which is from the input G1, G2, ... finally many elements. And then what you did was you could plug in the junctions Fi's. So what does it, how does it translate to in the case of hyperbolicity? It's basically saying that, so if you had a random geodesic segment as a building block, and you want to connect this with another building block somewhere, can you do that without huge cancellation? Yes, you can do. Why? If you allow me just a slight amount of angle deficiency, then the geodesic rays emanating from here and geodesic rays emanating from here, they have the intersection. So this is one instance of this almost closing lemma that I mentioned. That if you just take a random like geodesic, then it cannot like close up right after, but you can bring the forward trajectory very close to your beginning point arbitrarily closely. So that's the differential geometry version of this course argument. Okay, so now step 3, relating ER with CR. Okay. So basically, we want this sort of inequality. This is the goal. So for the upper bound, we will construct a map from CR times some linear index set. Okay, this will be actually epsilon r for some suitable constant, but I will not care about that too much, into BR. And seeing this direction of inequality, you should guarantee the injectivity. So if you're bringing like too many elements, but if you're clustering into just one element, it will not deduce any inequality. So we want a map that is almost injective. So how do we actually do? So here's a picture. So downstairs, there are a bunch of infinite geodesics that correspond to like various closed curves upstairs. So let's fix one curve. Then it will like even one curve will have lots of translates, but certainly at least one of them will be close to x0. Why? Because of the compactness. So if you have this curve, then at least this curve is like close to x0, like no more than m, like at some point, and then you just bring that the corresponding lift. Okay. Now then, that transformation is an element of G. So from this gamma, I chose 1G. So this is the way you choose the representative of the conjugacy class. So basically, from this, you choose 1G. But there's still another factor that you should bring. So what does I do? I does something like this. Sorry, I will fix this as x0 just to make sure. So these are fixed, and x0 is fixed. Now, if this gamma is long, we will see other orbit points of x0 that is also nearby gamma. What does it mean? Let's say you proceeded by 2m, and this point, it will be somewhere around here, but that's still close to that's still close to x0, like by the distance m. So it will still be close to another lift of x0, which is not the x0 tilde that I fixed. So I will still have another one. And if you proceed further by 2m, you will also get another one, which are all distinct because like this and this cannot match because I proceeded by 2m and then chose the one that's m close to that point. So basically, how many times you can do? You can do till the length of G divided by 2m or something. for these i's, you can choose another. You can choose another orbit point that you see close to the gamma, and then f gamma I will be gi inverse gi. So what did I do? All these conjugates represent the same conjugate class, right? Because I constructed all of them from the same geodesy. But I want to argue that these are all distinct in the level of group element. And also, if I choose them from distinct conjugate class, then the resulting element is also distinct. That is immediate, but distinctness of f gamma I for various I, this is something to be proven. So suppose f gamma I is same with f gamma prime I prime. If gamma and gamma prime are distinct, then the resulting group elements belong to distinct conjugate class, so they shouldn't be the same element. So it follows that gamma is gamma prime. Now, if I and I prime differ significantly, let's say I is greater than I prime. Originally, I should prove from this assumption, but for allowing some room of error, let's suppose this. Along this geodesy that represents gamma, I had x0 here, and there is gi x0, and there is gi prime x0. And this is gi x0, and gi prime x0 is somewhere here. So what do we get? So if I see this geodesy, let's fix this element as h. H is gi inverse gi prime. And because of this assumption, this has displacement at least m. Now the point is, if I take gi prime h x0, that's also nearby the geodesy drawn between gi prime x0 and ggi prime x0. This is just translating this configuration by h, and then you'll get another configuration like that. And then the hyperbolicity tells you that this is not evading away from the ultimate gamma. This is also uniformly close. So these are or uniformly close to gamma. So what do I get? So consequence is G is this H times some other group element. Okay, that's fine. This is just a equation for like any G and H, but with a special property that with the displacement smaller than r minus 2m. So basically, this displacement is around m, and the total length is like less than r. So this length is smaller than r minus 2m. So this is a non-trivial consequence that you obtain because both h beginning from gix0 and h squared beginning from gix0 are close to the progress a by g. Okay. So what's the contradiction? Actually, there's no contradiction. But so such g will come from this kind of construction. So this is in this kind of form. Come from h in Bm and this element from b to the r minus 2m. What's the matter? The population is around e to the hm. This population is around e to the hr minus 2m. So if you multiply them, you get e to the minus hm from e to the hr, right? So again, this is too complicated. Let's get back to F2. Basically, what I'm telling is, consider this kind of word, AABB and AABB. If this were F gamma and 0, okay, that's fine. But if you take F gamma 4, it means I shift to the right for like 4 steps and then declare the conjugate there. And it in this case, by coincidence, the conjugate is the same, ruining the injectivity, right? So if I conjugate this word by AABB, that's the same element. So I want to rule out this kind of possibility. How can I do that? This is too rare combination, having H and H. So it could have been something longer, like it could be H and some remaining thing. But the number of such combination is number of length 4 word times number of length r minus 8 words, which is compared to the combination of length r words, very negligible. That is why you can basically ignore such occurrence. So the key point is, again here, I will not define this function from CR, but sem minus some problematic set, which is gamma such that G is H times some other word, let's say S, where the displacement is almost additive, like as here, like the progress just doesn't cancel out, but it just adds up. And this is greater than like m or something. And basically, this population is comparably, compared to the population of CR, quite negligible. So you can just ignore them. Like you're just recruiting half of CR. And with the additional index, you construct F, and the injectivity holds on this domain. This is basically, so we will get CR sem minus this problematic set is smaller than okay, here epsilon was actually 1/2m, which is not that important, but and this is at least 0.5 or something, because this is negligible. This is how you prove the upper bound. Now the lower bound. For lower bound, you should construct the reverse direction of map from BR to CR. But this time, the map should be from BR to CR which is at most R21 map. Of course, there's another room of error. So there should be a multiplicative constant, but ignoring that. The map is straightforward. So if I bring one G, so G is here. So this time I'm worried about this kind of words. If I just plug in G into the conjugate class, I mean, G has its own conjugate class, so probably I can send it to that conjugate class. But what's the problem? If you see this word, the beginning and the ending subwords are canceling out each other. So the conjugate class will not actually carry the combination that you see at the head and the tail, because that's erased if you take the conjugate class. So I want to secure all information made by G. So I would know cancellation. So I will adjoin this secret F, again from phi square, psi phi, and psi square, such that it doesn't cancel out the previous progress made by G, nor the future progress made by G. If that's the case, it will honestly make a quasi-geodesic on the hyperbolic space. And this is almost the length of the closed geodesic that you get. So F is G sent to GF, where F is from this set, depending on. Now, why is this at most R21 map? F G is equal to Fg prime, i.e. GF. So the orbit made by GF and orbit made by G prime and F prime fellow travel. On X. In that case, so here's the gamma which is the same, which corresponds to the same conjugate class. G and F can be made here. Yeah. And perhaps G prime and F prime are making progresses elsewhere here. So they represent the same translate along gamma, but their beginning point is a bit different, because, considering that amounts to the conjugation. If that happens, so the conjugator is H, so GF is H times G prime F prime, H inverse. So in that case, only this can happen. Here is F prime G prime previously. So these are all aligned geodesics. So this point, this orbit point, should remain close to gamma. as well as this one, and so on. So if you see H, progress made by H, either it's along gamma or it's along the reversal of gamma, but it's not like somewhere like way out, like away from gamma, because all the points that you drew were close to gamma. Hence, this H is chosen from, H corresponds to these orbit points. Here's x0. Here is gx0. Along the length of G, you might have different orbit points that's close to this geodesy, but there are only linearly many orbit points. Why is this the case? Because you draw a bounded radius here. There are only bounded, like there are only finite amount of orbit points. You draw ball here. There's also finitely many. Here, finitely many. They cover all the orbit points that's within the neighborhood of this gamma during one cycle. Yeah. Sorry, this is. Yeah. This is. Oh, sorry. This is the contrast class. Yeah. Sorry. Hence, there's a ambiguity of the conjugator, but what I'm claiming is the conjugator should be between the orbit points that's close to the eventual direction because of our choice of no cancellation and alignment. Hence, like how many geodesy you can draw between orbit points within a period, that's almost proportional to the length of the period, which is the length of, which is r here. So there are k some constant r many choices of h. This is why the map f is almost r to 1, like there's a constant, which gives the upper bound. Is there any questions during the proof? Oh, right. Like in the free group, like in the extreme case of free group, it means. Oh, yeah. Okay. Yeah. In the free group case, yeah, it means like there's no like letter and its inverse like consecutively. Yeah. Exactly. Yeah. That's the case for free groups. Right. So for example, for free group, if G is like A, B, B or something, then F will be just like A or B, just not A inverse. Instead of what? What is the difference when it becomes Fn? What is the difficulty? For Fn, like I think it's as easy as in the case of F2. So everything is explicitly computed. So that's the take here, that for free groups, you don't have to like do this hard. You can just compute the number of like reduced words. So why do we do this? We are actually aiming at the actions on hyperbolicity spaces. But for free groups, like it's more straightforward, like how this goes on. But of course, like for free groups, there's more easier way to do. Okay, so I should wrap up for today's one. So what's remaining? So first, this is only for hyperbolic groups. So I consider proper co-compact action on hyperbolic spaces, which basically means G is hyperbolic group, right? But what about other groups? So for example, for cat0 groups, like for mapping class groups, some other groups. And also, what if the action is not co-compact? At least next time, at least I will prove for the cut surface case, probably not the general, like anti-dimensional case, but I will explain how this strategy can be generalized to these cases. And if time allows, I will also explain about subgroups. But today I'll stop here. Yeah.
Okay, so are there any questions?
Mm-hmm. Right. So this is a cost that we pay for this course argument. So if you rely on smooth dynamics, then you can actually bring these K1 and K2, like for example here and here, K1 prime and K1, K2 prime, as close to each other as you want. Right. So there's an honest limit. So for example, when the action is on Technion space or for for K-1 manifolds, there, for example, it's due to Hoblang and Mirzakhani, respectively, that the limit actually exists. But for this kind of course setting, like just discrete, like hyperbolic group acting on metric spaces, like delta hyperbolic spaces, this is not achieved yet. So for free group, let's say like there's an exact explicit asymptotics, and there we know that there's a limit, but the limit is not, so this K1 prime nor K2 prime is not 1. It's something else. So that depends on how hard you do it here. Yeah, there's, but sorry? In terms of the space. You can write it down in terms of the delta, the hyperbolicity constant and the diameter of the quotient in this case. Yeah.
Any other questions? If not, so let's thank the speaker.